Oh, now I'm live. I thought I was live this whole time. I've been live for 10 minutes. Let me start over. I was wondering why no one was in the chat. Let's see. Stream health is kind of poor. Analytics, no one's joined yet, but we just started. So let me give you the high-level overview of what I'm looking at here. We've got over here, you should see the charge curves of, what is it, the Silverado EV, and then we've got some Excel graphs up in the corner, some of the calculations, and the Bright Drop van that I'm working on, which has kind of been the same for a while, but I think we'll finally get some movement on it. And let's see, let's go to the charge curve real quick. So the question I'm trying to answer here is, what should you do? Should you drive really fast and then stop and charge for a long time? Or should you slow down and minimize your charging time, but then you're traveling slower so it takes longer to get there? What is the optimal speed? To do that, you kind of need three things. You need to know how much energy does the vehicle consume when it's driving at different speeds, how fast does it charge, and actually what your initial charge is and what your final charge is. So there's this charge curve, and you want to know where do you start and where do you end. Those are two parameters. And then what speed do you drive at when you're driving. And then your average speed is going to include your time driving, your detour time to get off the interstate to the charger, your time to get back onto the interstate, and the time you spent actually plugged in charging. And I estimate the detour time at around 5 minutes. So that is over here. Time of detour, 300 seconds, or 5 times 60. So you got 5 minutes to get on and off the interstate, which I timed it a few times and it was pretty close. It's maybe a little more on some of the more difficult to get to charging stations. And then the initial state of charge, almost all EVs charge really fast at first. But at the really low state of charge, say 0 to 5, they can be kind of slow. I know in the Tesla in particular, if you get into a charging station and you're less than 6%, it predicts that you're going to get there low, so it stops preconditioning the battery, so the battery's not warmed up, ready to go. And then when you get there, you plug in, it's got a slow charge, and then it's using that to warm up the battery, and you don't get up to speed until 10% or greater. So it's actually faster if you get in right around 6%. Plug in, and then you've eliminated this real low state of charge area. Oh, not that fast on this van. Yeah, this is the Silverado EV. It's a beast of a charger, which it's got the same batteries as the Bright Drop van. And maybe we can run those numbers a little later, but it would be really nice if they could charge as fast. But the Bright Drop van doesn't have the power split, so the Silverado can connect the two packs in series, so it jumps up to 800 volts, and it can charge them basically twice as fast. The Bright Drop van doesn't do that, so it derates it. But even then, it's not half of 350 because it's only 120, which I think I know why, and maybe we can look at those numbers and see why it's so low. So we've got our initial and our final state of charge and our driving speed. So I just locked in the initial state of charge at 6%. You can change it manually, but to only have 2 degrees of freedom, your final state of charge and your driving speed, makes it really easy to calculate and get a matrix of every possible combination of those two. So that's done over here. So here we have a matrix of driving speed in miles per hour, and state of charge at end of charging cycle. And then each one of these cells calculates at that, it says if we plug in 15 at speed and 12% at charge, what's our average speed? 14 miles per hour. And then you can see your average driving speed on a road trip. And the max, or the peak theoretical, is here. And let me highlight this at the same time. And here. So 62% charge to 62, and drive at 80 miles an hour. And I was really concerned with the bright drop being such a big van that you would have to drive it slow in order to get a good average speed, and then you'd be clogging up traffic on the interstate. But according to this, you could go anywhere from 65 to even 90 miles an hour if it'll do it, and you could get a really good average speed. But anything over 80, you're actually going slower. So 65 to 80 is kind of the sweet spot for this van. And then because it charges so slow, you have kind of a real wide state of charge. You could charge up a lot. Say you're somewhere at a grocery store and you got a lot of time to burn, or you're gonna go in and get something to eat. You don't have to worry about wasting time charging because you still got plenty of, you can still charge at a higher percent and still have a good average speed. Or if you're in a hurry and you want to get to the next stop where you're going to eat, you can just charge a little bit and still maintain a good average speed. Yeah, make it perfect for van life. Yep, nice and flexible. And it'll be kind of nice charging with a van because you can hang out in the back, fire up your Wi-Fi or your Starlink and chill out, get something to eat, make something to eat. And then this calculates it for you. So it says, here's your max average speed, driving speed, and charge 2%. And then here's a plot. So you can see here's your charge, and you got this nice peak here. So that's the all-wheel drive bright drop. Let's look at the Model Y. So the Model Y is a little peakier. You know, it doesn't have that nice broad band, and you'd have to drive 110 miles an hour and only charge to 50%, which it has kind of a bad charging curve. Let's look at that one. EV search. And this is EVXK, evknowledgeexchange.net, and they have really good specs, and they catalog everything really well. I'd seen it before in the past, but I hadn't really used it much. And then I was looking for charging curves. I went back and dived into it, and they got really good information here. Let's see, long range rear wheel drive. Most people get the all wheel drive long range. So let's look for that long range. L, maybe this is the new one. I've got the older one, so I'll put this one up just because I'm familiar with it. So here's a charging curve, and it does just like this. You plug in, it jumps up to 250 kilowatt, and it's awesome. And then a few seconds later, it's already tapering off, and it just tanks all the way down. It does not sustain a good charge for a long time at all. So that's why on this one, optimal is only, say, 50%, because after that, you're down less than 100 kilowatt. And in the winter, I've been driving, I don't even get 100 kilowatt at 50%. It's dropping below that already. But here's the cool thing, is the Model Y, max average speed is, I don't know if I said this already, 68.9. The Silverado is actually faster. So if you could go 115, which I know the ICE versions are governed at 100, not sure about the EV version, so you can't really go 115, but it's actually faster theoretically. In fact, let's look at 100. If you want 100, you could still, yeah, it's not that sensitive. So you can stay above 70 miles an hour average speed from a range of, say, driving 95 to 140 theoretical. But let's put it in a realistic range, say 85 in Texas to 65 in some of the other states. And you're right between 60 and 70 miles an hour average range. So yeah, if you did a cannonball run and you had a good charging network, you could actually beat a Tesla in a Silverado EV. But if you want to get crazy, the Taycan is the one to do. This thing's off the chart. Different models and trims have different top speeds. I'm only going out to 140. In fact, let's change it here. I don't think I labeled this, but this is my step. So if I go 10 mile an hour increments, yeah, so it goes out to 270 theoretical. Your max is 95 and it's at 150. So theoretically, you could average 95 miles an hour if you drove at 150 and you charged to 70% each time. That's crazy. But let's look at the charge curve on that. So models, search. And there's a bunch of them. I think they all kind of charge the same. So I'll pick the base model. Cheapest one here. Charging curves. So this thing is 250 flat all the way out to 50%. Let's look at a higher performance model and see if it's the same. What is like the top? I think it's this one. Yeah, 300. It'll sustain above 300 kilowatts all the way out to over 60%, which is just wild. That's crazy. And who knows, maybe it's degrading the battery too. You know, performance cars, they're okay letting it degrade a little bit so you can abuse it harder. But yeah, that's the best one for max average speed. Oh, change the subject a bit. Camper van layout. I have not been in there much lately, so it hasn't changed too much. I did have an idea that I wanted to go over maybe the next live and start modeling the actuators for these fold out wings. Of course, the simplest is you just do a fixed array, but let's go inside. You turn it into perspective view, and I have a 3D mouse and it lets you fly inside and you can see. So it's still got some kind of large monitor, speakers, a desk with audio interface. So basically this is everything you need to work, record, do studio, watch TV, and then the bed would fold out. And I was looking at a few different, I don't have the inverter in here. Oh, I hit it. But mounting a large inverter on the wall and then different batteries. I think this one, these are SOK batteries that could fit under the sofa bench area. And I might prefer that over like a rack mount. If you were in an accident, it would be easier to kind of wall this off and secure it down so that it doesn't go flying around the cab if you were in an accident. So I think it'd be a little safer. And then it would be lithium iron phosphate. So that would be safer, but still if it was a fire risk, you could kind of enclose it in a box that's semi-fireproof and resistant. And then on the wall, the camper, have that be the weak point where it would vent. So if something did go wrong, it would vent outside of the van and not into the cab. And then for the walls, I was thinking giving a good 3 inches of insulation and using wool. That I've heard that board, the insulation, I forget what you call it, that pink board. When you're driving, it rattles and squeaks a lot, makes a lot of noise. Pricing EcoFlow. Yes, I saw there, who was it? There's Grounded is doing a conversion, and then there's another company that did a really nice conversion. I don't know what they're going to do now that it's canceled, but they had a whole system by EcoFlow. It wasn't on the market yet, so they must have talked to EcoFlow and got like a custom or early production release. And it was an RV battery solar integrated system. It had everything included. That was probably one of the cleanest I've seen. I like EcoFlow in terms of they're real consumer friendly. Their prices are good. Their quality is good. They're not super high powered industrial, although they do have some of those home units. So I was looking at using what I used on the Cannonball run, so a large Solarc, just so I could have enough excess power to really charge the van quick. They come with a up to 19 kilowatt solar, or not 19 kilowatt 240 volt AC charger on the van, and so you could use a large Solarc inverter like a 15K, and you could charge it at 15 kilowatt. So let's say you stopped and you had to top off your van from your house battery, you could do it pretty quick. You wouldn't be stuck there for hours trickle charging it like on a smaller 5,000 watt or 7,000 watt system. But it doesn't matter, you can put whatever you want in here. And you can download the models a lot of times. I don't know about EcoFlow, but Solarc. Let's see, I think I've got it here. I did kind of organize the folders a little bit. Let's see. It's probably in CAD imports. No, downloaded content. So you've got the, this is the Victron inverter. They're really well built, but it doesn't quite have the total capacity of the larger ones. And then, where is, let's see. Here's a Solarc. Oh, the camper van version's already on the market. People have been using it. Oh, I got to go look that up then. Here's the Solarc. I think this is the 15K. Now, the ideal solution is you take the 2026 model year van, which I've heard there's a few of them out there. They're really hard to get. Maybe there's some more still stuck in Canada. And it has exportable power, so it has 7 kilowatt exportable, both 120 and split phase 240. So in that van, you don't need an inverter. All you need to do is charge the batteries. And at the Battery Expo here in Detroit a few months ago, I saw a company that has a DC to DC charger that does solar DC, or it could do solar DC right to the EV DC charger. So they make DC chargers for EVs and they do solar. And they can do it direct DC without having any AC conversion. It would still need a buffer battery, but you would keep everything DC voltage. And then if you had the exportable power on the van, that's all you need. So you have one small module that just charges the van, and then the van becomes the house battery. And that's probably the ideal solution. But there's only a handful of those vans that were ever made, and it's only model year 2026, which I thought they canceled production before 2026, so not sure. It looks like look for EcoFlow power kits, 5K VA 48 power system. Okay, nice. It's 48 volt. That's good. In fact, this is a walled off thing here, so I can just look here real quick. 5K VA 48 volt Eco Flow. Oh, this is the RV one. It looked like the home one. Oh, current connected. Here's the EcoFlow site. Yeah, these look pretty tricked. Yeah, I'll look more into this too and see. So yeah, so the kind of the van architecture, what I'm thinking is you have to create an account to get into Onshape, but once you're in, all this stuff is there. In fact, this isn't even my main account. This is just a secondary account I shared it with, just so I could interface with it the same way everyone else would interface with it. The only difference is I have read-write access, so I can change it here. But you can save the model out and then change it, do whatever you want with it in the free version. But everything you do in the free version is public. So just keep that in mind. For my company, I have a paid version, and we use that internally. It's a totally different account. And then you get revision control and a lot of product data management features and stuff like that. But as far as the modeling goes, it's all the same. So the cool thing is, and this is the idea with it being open source and in Onshape, is once you build it, if there's any part you want, you don't have to worry about getting documents on it. You could look at the part, get the part number, go right to Onshape, pull up the part, the drawing, the vendor. You know, vendors could even bid on it and then put their price into Onshape, so it'd be in the metadata for that part. So you could see what the price is, who to buy it from, and if they're no longer making the part, maybe you could print it. If you can't print it, it should have a detailed engineering drawing. You just take the drawing to a machine shop, say, hey, can you make this part? They say, sure, it's going to cost this much. And then the other thing, as I found out, is each one of these parts, and you can't see it, but at the top, the address, you can turn that into a QR code, and you could take that 2D QR code, put it on the part. You could literally scan the part with your phone, and then it would take you right to that part in Onshape. Let's see. So let's take, I think I kind of tried this. So let's take the floor here. And so with Onshape, it's actually not bad. It has this little AI advisor, which is kind of helps you weed through all the long-winded answers and just get right to what you want. So I asked it earlier, how do you add an image to a part? It says do it as a decal. Part Studio. Sometimes if you don't know where it is, you can just search for the tool and type decal, and you can click it here, or it'll highlight where that tool is at. So we can go decal, brings up the interface here. We click that part, select an image, and I think this is the right one I downloaded. Let's make it say 100 millimeters or 4 inches in size, still kind of large. So now this part has a decal on it. It was made in Chrome, so it's got their little dinosaur logo. So depending on what device you're using, if you scan this with your phone, it should take you right to this part. All of what you're showing now is also making it available for free on this Onshape website. Yep, everything I do in here, you have full access to it. You can't overwrite my copy, but you can make a copy of it and do whatever you want with it. So if you scan that, maybe give it a try. It might take you right to it without logging in, and then if you want to actually save out your own version of it, it'll say, hey, you got to create an account, go through all the steps. Let's see. Yeah, the stream is still working good. It looks like it started off real high at 4K, and then it kind of dropped down a little bit. But it looks like it just kind of throttles, or maybe my connection isn't quite as stable. Someone was telling me that YouTube will do that, and then once it fully processes it, then it'll pump it out at 4K. So hopefully you can see kind of this quad display. It's a high enough resolution that you can see everything. And there's lots of videos on how to do Onshape, but it might be of value to just kind of give a quick walkthrough at some point, just a short 5-minute video on how to get in, and then the quick tour of where everything is and how to use it. It's made by it was started by the same guys that started SolidWorks, so it's kind of intuitive to a SolidWorks user, although their product data management, how you check things in, check them out, keep revision control is different, but way better in Onshape. I'd say SolidWorks a little bit better in terms of modeling capability, but holistically I prefer Onshape at this point, just because it's so easy to keep track of revisions. There's no checking in, checking out. When I'm working with the team on other stuff, we can have the same part open at the same time. Someone can be making it longer, I can be putting a chamfer on it simultaneously, and then the only thing you can't do is both work on the print or the drawing at the same time. So it's pretty powerful, and it keeps track with infinite undos. So that's Onshape. So back to the charging curves. I can't see the numbers because I'm on my phone. Let's see. Everything's kind of small. Let me switch over to this mode here. So now it's just one screen at a time. So it should be larger. You'll be able to see the Excel sheet. And hopefully the background music, I don't know, how's it sound? Is it too loud? Not loud enough? Annoying? I'll give a quick overview of the Excel calculations. So basically all the formulas and everything are in this column, and then everything is feeding into this, or it's some derivative of this. And if you click in the cell, I've named all the cells the same thing as the name in this column. So if you're looking at a formula, you can double click, see where it's pulling it, and you can see, you know, this is PFM power front motor, and then the descriptions are over here. And I have the units, and then sometimes I convert them into English units just for kind of a gut feel. Music good, good volume. All right, cool. So I got, you know, the battery, the motor portion, drivetrain efficiency. This is an estimate, kind of approximation. Transmission, you know, the gear ratio, torque, and then the vehicle parameters, speed, road mass, torque at the road. And then I've got drag calculations and another set of drag calculations from coast down coefficients. And I pull that from the government website here. So these are, you know, it's a polynomial fit, you know, good old y equals constant plus a constant times x plus a constant times x squared. And so these are the constants that go in front of the x terms. And then x is your velocity. And then I'm doing the arrow approach, which is aerodynamic drag is 1/2 rho v squared times frontal area and coefficient of drag. And those are the numbers there. I don't have them for every vehicle. I think I added this earlier. Delete that. I don't have them for every well, no, I do here, but you can't get them for every vehicle. So some of them I had to estimate, like the Bright Drop van estimated at 0.33. Model Y is pretty good, 0.22. Taycan is pretty good. Silverado EV is surprisingly good for a truck. Hummer is surprisingly bad. But and then the coast down coefficients, those come from the government website, and all passenger cars are required to go through that testing, so they have them. The Bright Drop van is not a passenger car, so they don't have that data for it. So I had to fall back to the Aero coast down. And so this feeds in to say, what is the power to drive the vehicle? And the power, you have the total drag force, which is drag force and the rolling resistance. So we just looked at the drag force, and the rolling resistance is kind of just an estimate. It's the mass times this coefficient of rolling resistance, which is kind of an estimate for different vehicles. And it's mostly based on the tire. So a typical good efficient tire is 0.01, and like a semi or a more efficient tire, a higher PSI road tire could be 0.008 or even less, I think. So the Taycan and Model Y I put a 0.008, and then the truck I put a 0.001. But if you've got like the all-terrain tires or the off-road tires, this goes way up and it kills your efficiency. So, but all the descriptions are here, and those are used to calculate the power to drive the vehicle. And I use that to generate these range plots. So this is your driving speed, and this is your range based on that speed. So for this particular vehicle, if you wanted to maximize your range, you should drive around 25 miles an hour. And that would theoretically get you the best range. Although these plots are not very accurate at both extremes. At the extreme low, it's very sensitive to parasitic losses and drag, rolling resistance. A small change or just turning the AC on and off can have huge effects here. And then as you get to the extreme, you're extrapolating data because you have these coast down coefficients that were calculated at maybe 65 to 0, and you're taking that data and you're projecting it out to a theoretical 100 miles an hour, so you've got some error there. Yeah, but definitely in the comments, all-terrain tires make a lot of difference. And then this plot here is kind of a cross-section of that big matrix here. So if you just want to look at one particular speed, so let's say we go back to, let's go to the van, since we're looking at the van, and you're going to drive it at, let's say, 75 miles an hour. So it should get you pretty close to the peak max speed. So put in 75 here, and we're going to charge it to, what was the charge? The ideal charge percent. 62%. So we'll put in 62. Now all these numbers are calculated at that speed and that state of charge, although most of them aren't a function of state of charge. It's just the speed is driving a lot. And then if we look at average vehicle speed as a function of driving speed, and you see one zero here across the bottom, that's the coast down, which we don't have those coefficients for the bright drop, so it's just 0. And here's average speed. So you could average 50 miles an hour at 80 miles an hour, and you can kind of see the window of, you know, if you start driving too fast, you start losing. If you start driving slower, you start losing range, or not range, you start lowering your average speed. So really you want to be 70 miles, 75 right at the speed limit. Most interstates is perfect for this van. And then if you want to know, well, how far can I go between charges, here's the vehicle range, and this green line, this is some user data someone did on a bright drop van, and so that's actual data, and then this plot is my theoretical curve. So you can see he got, if I hover over there, 440 miles at 46 miles an hour. So he took the bright drop van really far, which is impressive. But if you slow down even more, you could go really far. So if you were doing an absolute range test, you know, and you went 20, 25 miles an hour, you could drive that thing for days and go, you know, 600 miles. And of course, with the AC off and everything like that, I think I put a AC load of 625 watts, which is what I kind of measured in the Model Y. But let's just say you turn that off. You're gonna have some accessory load, lights and stuff. Let's just say it's at 100. Now you could, you know, it doesn't change much at 20, but maybe still 700 mile range. Who knows? Who knows what you could do? But they did it in a Silverado. They went 1,000 miles in it. Silverado EV. They had the AC off, so let's drop that down to say 100. And they drove 20 miles an hour. So here at 20, coast down approach is just under 1,000 miles. And they overinflated the tires, so they put them to max pressure, and they used the baldest tires they could get. So they had some old worn out tires, and they overpressurized them. So if we drop this down to say, I don't know if 6 is the minimum or 7, I forget what kind of the limit is on that. Oh, I did the wrong one. Silverado EV. Oh no, let's just drop it down to 0.008 like the truck tires. Yeah, you're still not quite to 1,000. Oh, you know what else they did? They used more of the battery. So 212 kilowatt hours is the rated battery capacity. It's not the actual. The actual is, what is it? I think it's like 40 something, 45 maybe. So that's the battery's brand new. You don't drain it fast. Everything's perfect, ideal. It's not cold. You could theoretically get 245, I think. And then it puts us into, at 20 miles an hour, it gets us into that 1,000 mile range. So it does look doable if you really push it to go 1,000 miles. And they did it, so it has to be doable. Let me undo all those changes. All right, I think I undid everything. And then yeah, you have your motor torque, power versus speed. They don't line up because there's different gear ratios, but essentially you have your power ramps up as the speed ramps up, then you max power your motor. You can't exceed a power. It's kind of a thermal limit, and it actually degrades a little bit as you stretch out to the extreme just because of the cooling. And then your torque, you have max torque, and then when it hits that max power, you drop off on your torque, which That's another interesting thing because the Bright Drop does have the same motors as the Hummer. You've got some 0 to 60 times down here. Let's see, Bright Drop van, aero drag, distance, or speed in miles per hour. So you hit, I highlight them, 60 miles an hour in about 8 seconds. But I think I've heard that it's not really that fast. But if you unlock the motors and you ran it, because it has the same motors as the dual motor Silverado. So let's just say we took the Silverado motors and put them in the Bright Drop van. So the motors are now equal to the Silverado EV, both in torque and power. Yeah, let's see if there's anything else we need to change. I don't think we need to change anything else. We'll see. But now, this is the theoretical 0 to 60 time of the Bright Drop van. No payload, just dry. You're looking at 3.6 seconds. I mean, it weighs the same as the Hummer. So it's the same weight as a Hummer. And if it's got the dual motor version, not the 3 motor version, it makes sense. Because the Hummer does, what, 2 seconds? Or is it 3? 3 seconds. So this is probably overestimating it, but could you imagine a sub 4 second 0 to 60 time in a van the size of a FedEx box truck? That would be wild. I'm sure someone at some point will unlock the software on it and actually do it. I like to keep my warranty, so I would probably not be the one to do it. And that's another thing too with the this build on the camper is there's no plans to make any kind of modifications to the van itself. So the charging would be you literally plug in your charger into the van through some kind of pass-through port. So you're not tying into the charging, you're not tricking the battery. If you connect into the battery, you're going to mess with the battery management system, the range calculations. You could overcharge, you could mess up all kinds of things. So the vehicle needs to know from its designed communication port what's coming in and going out so that it can manage everything. So yeah, no modifications to the van except for cosmetic stuff. Obviously a bunch of rivet nuts and drilling and stuff on the structure, and it's got a pretty strong bulkhead in the rear. It's mostly stamped, but it's still pretty rigid. And then in the front, it's got extruded aluminum bulkhead that's really stout. So if you tie into that, you're good. And then internally, it's got these rails, extruded aluminum, that are pretty stout, but not as strong. So the bolts are exposed. So ideally, you tie into those, and then your main support, if you had anything heavy, will go to the front and the rear bulkhead. So the plan with the actuators is to have them tie into the rear bulkhead structurally, and the front ones to tie into that front bulkhead, and then just support down along the panels for the stationary panel right to there's bolts that you can access here. You can take the existing one out, put in a plate, bolt in a bracket. So matching that bolt pattern for sure. Let's see. What else? Yeah, I don't think I'm going to do any modeling today, but I really just wanted to look at the average speed, those calculations, and then thinking through the best way to kind of describe it in a short 5-10 minute YouTube video. It's a question I always had, so that's why I ran the numbers, is, what speed should you drive at when you're on a road trip? You're in the car and you're saying, should I slow down and then I'll have more battery when I get to the charge station, or should I just go as fast as I can? And this kind of answers that for whatever vehicle you have. And then you can paste in the charge curve data. So I just pasted this in from EV Knowledge Exchange for the different vehicles, and it's linked back to whatever you select here. So if you select, say, the Taycan, and then you go here, it's saying, hey, the Taycan's selected, so that means it's pulling all these values into this, and it's getting a time and a numerical value because the time values are weird. And then I curve fit it with fourth order polynomial, so you can see One curve is the actual data, and then you can see the curve fit kind of overlaid. So it's not exact, but the curve fit lets me run the calculations at any point along that and kind of integrate all those data points, so we don't have to do lookup tables and then have perfect match with exact state of charge. So once I have the curve fit numbers, those get pulled back into here. And let's see, where are they calculated at? State of charge. So time, so this is the charge time from initial to final. And what it does is it uses those coefficients and it pulls them in and it calculates. Essentially, one is your starting percent and then your final percent, and it calculates the time. So this is the minus, so it's subtracting off the time that would take to get from 0 to 6% because you're not starting at 0 and then going to 62, and that gives you your time. Let's see. And I have some references here. And I'll put this in Onshape. I'll update it here, the location. Oh man, I was talking about the model and I wasn't showing it. Let me go back to the quad screen. Okay, so now you can see it. Presenting to nothing here. So I will put in Excel tools in this folder here. So kind of the layout real quick of Onshape is you have all these tabs across the bottom, and if you want them in a vertical format that's easier to sort and filter, you click this here. You can filter on just parts, assemblies, drawings, images, etc. So we'll go clear all filters and Excel tools. So here's the Excel tool, version 1.074. I'm working on version 1.1, so I'll upload it in here, and then you go to Onshape, go to Excel tools, you should see the latest version here, and that includes the powertrain, these charge curves, coast down coefficients, US city and highway drive cycles using two different coast down, or the coast down and the arrow approach, the specs on the Maxion panels plan to use, and the latest data on pricing. So before the end of the year, it got pretty cheap. Now the Costco discount is gone, and you still get this $21,000 on a model 2025. But if you jump up to the model year 2026, it drops down to $14,000. You've got the same MSRP, but you only get $14,000 discount. One dealer said they put an extra $1,000 on it, but there's no Costco discount. So you're looking at, let's see, it started at 60 and then it went down a little bit before the end of the year, and then now it's back up at 68. But you do get more than just the exportable power on the 2026. You get a little bit more modern electronics, I think, and some other good stuff. And who knows, the exportable power module is probably the same as what's in the trucks. And maybe in the future there would be some way to retrofit it. I don't know. You definitely couldn't on the 2025. It wasn't really architected in, as far as I know. But 2026 it was. So that's kind of the spreadsheet. If you have any questions, drop them in the comments, of course. Or join the Discord. I think I've got a link to Onshape and Discord in the description on this live. And I think the next live will be going over these actuators and gears and how we can make those panels fold out, extend down and around the van. And we could also do multiple configurations. We might have one configuration where it's just the panels on top with that support structure. And the thought is to use mostly sheet metal, something that could be laser cut really quick, laser cut bent, or maybe standard extruded aluminum. But I want to keep it economical to make, but at the same time, some of that extruded aluminum can get pretty expensive. So if you're doing any kind of volume, it's actually cheaper to just buy sheet aluminum, have it laser cut real quick, and then assemble it or weld it together. And you can get more rigid if you fully box in sheet metal. You can get some pretty nice structures. And it's kind of the plan too, is to model it after airplane fabrication in terms of how they do their wings with the sheet metal for just the strength and to handle the wind load. Because when this thing's open, a gust of wind comes along, it could rip it off if it's not built really strong. So that's kind of what I was thinking. Oh yeah, I haven't checked the comments lately. So, do I have the terrain elevation data built into the Excel sheet? I have it, but it's not integrated into the powertrain. I have a placeholder for it, but this one is, it's been a while since I used it, but you put in your numbers and your total elevation up and your total elevation down, which you can get from Google Earth, and then it tells you how it's going to affect your range. So maybe I could tie that back into the range. So you could say, hey, I'm going to go up 13,000 feet and down 10,000. What's my new range? So then you're calculating your range, including elevation. So it's there, but it's not integrated yet. The panels, they're not quite flexible. So these panels, SunPower said that they could give me some of their early panels that they plan to go into production with. Not SunPower, it's now Maxeon. And they're industrial semi-flexible panels. They're not really designed to flex. They're called Maxeon Air. And they're originally designed for rooftop installations where it's a peel and stick panel. So it's an industrial panel with a thin sheet of glass on top. And the idea is you peel off and you stick it on, you have those fabric roofs that can't handle much weight. So you can't really install solar on it. In fact, let me just pull it up real quick. Get a picture of it. These guys say they're for sale, but they're not. Let's see. Nope. Yeah, I don't know where the website is for that's actual. Well, here's what they're going to look like. They're not really for sale yet. I don't know why they're taking pre-orders. But it's an industrial panel, 330 watts nominally, although you can get 340. And I think it's like 4mm thick. Oh no, they did get some. Maybe some early production runs. So yeah, they're no. Okay, they drilled through it. Okay. I haven't looked in a while, but yeah, this is kind of the panel. So that is kind of a flexible looking panel. So I'll have to look into it and see. It's been a while since I contacted Maxeon, but those are the panels. They're real lightweight. So the idea is to stick them to a sheet aluminum, and then that should help kind of conduct out heat and keep the whole structure really light. You could go rigid panels with glass, but then it gets kind of heavy. I see some with 700 watts bifacial. Yeah, bifacial is a good idea, especially if you had slide out instead of actuating, because then you're going to get a lot of that reflected and you don't need the solar tracking as much. So bifacial would be a good idea too. Yeah, Maxeon are expensive, yes. Although now you can get their, let's see, SunPower 100 watt flexible. Yeah, they're really cheap right now. They don't make them anymore, so they're just selling off the old stock. But they were like 125, and you get them all day long for 125. So if you're going to get a flexible panel, I would definitely get these. In fact, I think I have an Amazon affiliate link I should probably put in there, so I can get like $2 for everyone that buys one or something. But yeah, that's pretty much it for now. So I will sign off, and I'll talk to you guys later.